Hi everybody, this video will cover section 2 of chapter 3, and here we are going to talk about compound interest. Specifically, we're going to talk about compound interest, and then a special case of compound interest, which is what we call continuous compound interest, basically the best we can do. Then we will talk about growth in time, or specifically how much time it will take for a certain account to reach a certain goal. We will present the idea of annual percentage yield, which is a tool which we can use to compare two different accounts, and then we will talk about some applications which will serve you well in the second part of your homework. Okay, so what is compound interest? Compound interest is an account where not just the principal earns interest, but the interest that you earned after a period of time, called the compounding period, will also begin to earn interest. So we say that it's where interest earns interest, which, yes, is interesting. So how does this work? Well, interest that is paid is reinvested, and this is called compound interest. After a certain compounding period, the interest earned is added to the principal. So the principal and the interest earns interest. I sound like a broken record. The frequency at which this occurs is called a compounding frequency, and we will call it that M. And the rate per compounding period is found by taking the actual annual interest rate and dividing it by the compounding frequency, or the number of compounding periods per year. For example, suppose that you are compounding quarterly. That means that your interest is going to be computed and added to the principal each 3 months. If you are compounding semi-annually, twice a year, that means that the interest will be computed and then added to the principal every 6 months. And if you are compounding monthly, the interest is then computed and added to the principal every month. How is the interest computed? It is computed using the simple interest formula that we talked about in our last section. And this brings us to our first example. Suppose that we have $100,000 and it's invested into an account that pays 6% annual interest, which is compounded annually. How much will you have for the end of 1 year? Well, this actually, since we're compounding it annually and we're going to be done at the end of 1 year, this really is a simple interest problem. So the equation that governs this is going to be our simple interest equation. A is equal to P times 1 plus RT. So we are investing $1,000. That is P. P is $1,000. Our interest rate is 6%. If we divide that by 100, we will get our decimal value, which is going to be 0.06. Since we are compounding annually, M is equal to 1, and T is also equal to, well, we're not going to worry about M right now, but T is equal to 1. Okay, so we can put all these values into our formula, and we have that A is going to be equal to 1,000 times 1 plus 0.06 times 1, and that will be 1,000 times 1.06, and that will be $1,060. And let's go to our next example, which is the exact same problem, but we are going to compound monthly. And let's see how this works. First, let's actually write down what our answer was for the first part. That was $1,060. And this is how this works. So we are investing $100,000 into an account that pays 6% annual interest, but it's compounded monthly. So every single month we are going to compute our interest and add it to the principal. And our question is, how much will we have after 1 year? So what we're going to do is we're going to compute we are going to compute our interest, compute our future value after 1 month. That will be our new present value. Then we're going to use that to compute our new future value after 1 month. And that will be our new present value. We're going to do that basically 12 times. So here we are at month 1. And let's say that our future value, I'm going to call A1, and that is going to be equal to our principal, which is $1,000, times 1 plus our interest rate, which is 0.06 0.06 times the duration of the loan, which is 1/12 of a year, since we're only going for a month. That is going to be equal to $1,000 times 1.005, because 0.06 divided by 12 is 0.05. Add 1 to it. That's what we have. And this right here is our expression. This right here is our future value after 1 month. And this also is going to become our new principal for month 2. So this was month 1. This right here will be our new principal for month 2. So for month 2, we will have that the future value after the second month is going to be equal to our new principal, which is 1,000 times 1.005, and we are going to multiply that by 1 plus our interest rate, 0.06, times 1/12, and that of course is going to be 1.005. So what we're going to have is that A2 is 1,000 times 1.005 times 1.005, or 1,000 times 1.005 squared. Okay, so that's month 2. You'll never guess what we're going to have for month 3. Month 3, well, you can probably notice the pattern. We have 1,000 times 1.005 for month 1. For this one, it is squared. It's not too much of a stretch to guess that for A3, we are going to have 1,000 times 1.005 cubed. And then finally, for the end of 1 year, month 12, we will have that A12, which is actually our future value, is going to be equal to 1,000 times 1.005 raised to the 12th power. And that will give us $1,061.67, which will round to $1,061.68. And okay, and now we want to compare this to what we had when we just compounded annually. And notice if we compound more often, we actually make more money. Here we actually made an additional $1.68, which isn't great, but you know, it's, hey man, money's money, right? Okay, but notice notice what's going on here is that we actually have this exponential thing going on, and that is the basis behind the compound interest formula. Here it is. Your future value is going to be equal to your present value times 1 plus your interest rate divided by your compounding frequency. This actually should say compounding frequency. And then this will be raised to m times t, where once again m is your compounding frequency and t is in years. Now, in some cases, you will find that this equation looks as follows. A is equal to P times 1 plus I raised to the nth power. In this particular case, I is equal to R over M. I is what we call the interest rate per compounding period, and that will be your annual rate divided by the divided by your compounding frequency. And then finally, let me write this again, A is equal to P times 1 plus I raised to the nth power. N is your total number of compounding payments, which of course is the number of compounding payments periods per year, or your compound frequency, times time. And let's go and take a look at this particular problem. Here, we are going to look at the same investment for different compounding frequencies. First, we're going to look at it for annual compound, if you're compounding annually, then if we're compounding quarterly, and then if we're compounding monthly. And since I don't have enough room here, we're going to go ahead and do this in OneNote. Okay, so here we are, and the first problem is, for our first problem, we are depositing $1,000, or we are investing $1,000 at 6%, and we want to know how much we're going to have after 5 years if we compound annually. And for all of these, we are going to use the exact same equation. That is going to be that A is equal to P times 1 plus R divided by M raised to the MT power. Now in this particular case, well, for all these cases, P is equal to $1,000. R is equal to 6%, which as a decimal is 0.06. T will always be 5 years, so T is 5. And since we're compounding annually, M is equal to 1. And so we can just go ahead and substitute all this stuff into our equation. And that will be that A is equal to 1,000 times 1 plus 0.06 divided by 1 raised to the 1 times 5 power, because remember T is 5. And now simplifying this, we will have that A is equal to $1,000. Okay, well 0.06 divided by 1 is just simply 1. If you add 1 to that, you're going to have 1.06, and since 1 times 5 is 5, you're going to have 1.06 to the 5th power, and that will give you 1,338.225, which will round to $1,338.23. Okay, so this right here is A. Now for B, the only difference is instead of M being equal to 1, M is equal to 4. So here we're going to have that A is equal to 1,000 times 1 plus 0.06 divided by 4 raised to the M, which is 4, times T, which is 5 power. Simplifying this, we will have 1,000. Now 0.06 divided by 4 is 0.015. Add 1 to that, you are going to get 1.015 raised to the 4 times 5 power, which is 20. And if you knock that out in your calculator, you will get, at least to the third digit, $1,346.855, and that is equal to $1,346.86. So notice that we've made a little bit more than $8 by compounding quarterly instead of annually. Okay, but that one, nonetheless, that is our answer for B. For C, now M is equal to 12. So now we're going to have that A is equal to 1,000 times 1 plus 0.06 divided by 12 raised to the 12 times 5 power. So that's a pretty big exponent. And that's going to be equal to 1,000. Now 0.06 divided by 12 is going to be 0.005. Add 1 to that, and you're going to have 1.005 raised to the 12 times 5 power. 12 times 5 is 60. And if you compute that, you are going to have an answer of $1,348.50. Actually, I'm sorry, $0.850. $1,348.850, and of course that will round to $1,348.85. So notice here we got an increase of over $8. $8 and change. Here we have an increase of $1.85. and 99 cents. That's it. So notice that the increases are decreasing as we continue on. As a matter of fact, as we compound more and more often, we are going to approach some limiting factor, and that limiting factor is what we get when we reach continuous compounding. And let's talk about that. Okay, continuous compounding, and as we mentioned before, as the compounding frequency increases, the interest earned becomes smaller and smaller, and it approaches some limiting factor or some limiting value. What is that value? This is the value, or this is the equation that determines the value. This is what we call continuous compound interest. And here, if P is invested at an annual rate R for T years, then the amount that you're going to earn is going to be equal to P times E raised to the RT power. So this is continuous compounding. So if you see the word continuous compounding in your question, this is what you're going to use. If it says it's compounding monthly, daily, or some other time period, what you're going to use is that is going to be the equation A is equal to P1 plus R over M raised to the MT power. Okay, so how does continuous compounding compare to a scenario where we're compounding quite often? Well, they should be pretty close to the same. Let's go ahead and find out. So here we have an account that is going to last for 2 years, so T is equal to 2. We're investing $8,000 into it, so P is equal to $8,000. And then our interest rate is 9%. That's a little better, which is equal to is equal to 9 divided by 100, which of course is equal to 0.09 as a decimal. I was kind of getting ahead of myself there. And now we want to know what our return is going to be if we compound daily. Well, since we're compounding daily, we know we want to use this formula. A is equal to P times 1 plus R over M raised to the MT power. Now there's one piece of information that I forgot to give you, and that is how many years are in how many days we're going to assume is in the year, and we're going to assume that 365 days equals 1 year. Okay, so with that in mind, we know what M is. M is going to be 365. Making those substitutions, we will have that A is equal to 8,000 times 1 plus 0.09 divided by 365. That is our interest rate over the compounding period, raised to the number of payments, which is going to be 365, one payment per year, times 2 years. And that will give us an answer of 9,577.526, which will round to $9,577.53. Okay, so what about if we're compounding continuously? Well, if that's the case, then our equation is going to be A is equal to P times E to the RT, where E is Euler's number. And making those substitutions, we're going to have that A is equal to 8,000 times E to the R, which is going to be 0.09, times T, which is 2. Okay, and that is going to be equal to $9,577 $9,577.738, and that will round to $9,577.74. So notice the only gain that we have is about 21 cents. So once again, as we compound more often, we are going to get close to the continuously compounding case, but that is the best that we can possibly do. All right, growth in time. Now, one of the things that you're going to be asking yourself when you do your personal financial planning is, well, if you want to buy a house and you need a down payment, how much do I need to invest now so that I can have a down payment of whatever, probably if it's a $200,000 house, probably $40,000, say in 6 months? Or how much do I need to deposit now so that I will have $100,000 in 17 years when my kids are going to go to college? How much do I need to deposit now so I have enough money to retire on? These are the kind of questions that we might be asking. The other kind of question that we might be asking is, well, how much, if I deposit X number of dollars now into this account, how long will it take for me to reach my financial goal? So the financial goal is for your money to increase by a factor of 2. The question would be, well, how long would it take for my investment to increase by a factor of 2? Although those are tools for comparing different loans and investment products, or also to make sure that your financial goals are somewhat reasonable. And so the rest of this, or the next part of this video, we're going to talk about how to determine the growth time for various investments, and also how to determine the interest rate associated with various investments. So here's our first example. Here we have $10,000. We wanted to grow to $25,000, and we have an account that pays an interest rate of 8%. And the question that we want to ask is, well, how long would it take $10,000 to grow to $25,000 if we actually compound that 8% semi-annually, i.e. twice a year? Well, let's go ahead and see if we can figure this out. Well, once again, the equation for any time if you're not compounding continuously, or if you're compounding over a period of time, is going to be A is equal to P times 1 plus R over M raised to the M T power. Okay, since we're compounding semi-annually, M is equal to 2. R is equal to 0.08, that's 8% divided by 100. A is equal to 10,000. P is equal to 25,000. So with all that, we can set up our equation. We are going to have $25,000 for A. That's going to be equal to $10,000 for P times 1 plus R, which is 0.08, divided by 2, since we're compounding semi-annually, raised to the 2 times T power, which is what we're trying to figure out. Okay. Oh, and this, I made the exact same mistake in class. Can't believe it. This is not 1,000. This should be 10,000. So we have 1, 2, 3, 4. Okay, so the first thing that we can do is we can divide both sides by $10,000. And if we do, on the left-hand side, we're going to get 2.5. On the right-hand side, these cancel, and we're left with 1 plus 0.08 over 2 to the 2t. But we can work on that a little bit. So we're going to have 1 plus 0.08 over 2 is going to be 0.04 raised to the 2 times t power. And we can simplify that some more, and then we will have that 2.5 is equal to 1.04 times t times 2t. And there we are. So we're not done yet. Now that we got it to this point, we actually need to take the log of both sides, preferably the common log. That will give us that the log of 2.5 is equal to the log of 1.04 raised to the 2t power. Now I can use the power property of the logarithm, which says that the log of a to the r can be rewritten as r times the log of a, and I can write the right hand side as 2 times t times the common log of 1.04. And of course that will be equal to the common log of 2.5. We're going to divide both sides by 2 times the log of 1.04. 2 log 1.04. The 2's cancel, the logs cancel, we're left with 2, and that's going to be equal to the log of 2.5 divided by 2 times the common log of 1.04, and that will give us a value for t of 11.68 years. So t will be equal to 11.68 years. Okay, for that compounding continuously, well, if that's the case, then our equation is going to be that A is equal to P times E to the RT. Everything we have is listed right here. So we're going to have that 25,000 is equal to 10,000 times E to the 0.08 times T. Okay? Once again, we're going to divide both sides by $10,000. And that will give us that 2.5 is equal to E to the 0.08 T power. Okay, now we can take the natural log of both sides. Actually, let me rewrite this over here. E to the 0.8 T. Okay, now I can take the natural log of both sides. And why do I want to do that? Well, because the natural log of E is actually equal to 1. And then I want to make use of the power property of the logarithm, the exact same power property that's here. And that's going to give me that the natural log of 2.5 is equal to 0.8 times t times the natural log of e. Well, the natural log of e is equal to 1, so this basically goes away. We can divide both sides by 0.08 t, and this is going to be 0.08 t. And so now we have natural log of 2.5 is equal to 0.08 t times the natural log of e, which is 1, and now we can solve for t, and that is that t is equal to the natural log of 2.5 divided by 0.08, and that will give us 11.45 years. And since compounding continuously gives us the biggest advantage of compounding, we would expect that we would reach $25,000 faster if we compounded continuously relative to compounding on it semi-annually. Okay, our next collection of problems are designed to help you in your homework. So here we want to know how much your new parents should invest at 8% compounded annually, so they will have $80,000 towards their child's college education in 17 years. Which will cover basically half of their undergraduate career. Okay, so once again, we are compounding annually. That means we're going to use this formula. PA is equal to P times 1 plus R divided by M times MT. Okay, cool. We know that P is $8,000. Oh, no, we know that A is $8,000. That's how much they want to have in 17 years. We are trying to find P. We know that T is 17 years. We know that the interest rate is 8%, so R is going to be 8%, which is also equal to 0.08. And since we are compounding annually, M will be equal to 1. So we will have that $80,000 is equal to P, we don't know what P is yet, times 1 plus 0.08 for R, 0.08 for R, divided by 1, raised to the 1 times 17 years powers. Okay, well, we can actually work with this. 0.08 divided by 1 is, well, that's just 0.08. Adding 1 to it, you're going to have 1.08. So this will be equal to P times 1.08 raised to the 1 times 17th power, or simply the 17th power. And that's going to be $1,000. And now we can go ahead and solve for P. We can divide both sides by 1.08 raised to the 17th power. 1.08 raised to the 17th power. And that will give us that P is equal to 8,000 divided by 1.08 raised to the 17th power. And that means that we would need, that should be 17, so I don't know if you can read that or not. And that means that P, or the amount that we need to deposit, is going to be $21,621.516, which will round to $21,621.52. For our next problem, we are compounding continuously, and we want to find the interest rate as a percentage to 3 decimals. So since we're compounding continuously, our equation is going to be A is equal to P times e to the RT. P is $20,000, A is $47,977.51, and T is 84 months, which is basically 7 years. So we are going to have that 47,977.51 is equal to 20,000 times e to the R, we don't know what that is, times t, and if t is 84 months, remember that has to be in years. This is going to be equal to 7 years. 84 months is equal to 1 year divided by 12 months, and this will give us 7 years. So in this case, we're going to have e to the R times 7. This is our A, this is our P, here is our R, our unknown, and T is 7. Okay, well, once again, we can divide both sides by 20,000. And if we do, we are going to have 2.398875 is equal to e to the 7t. I'm now going to take the natural log of both sides, and that will give me that then I will have that the natural log of 2.398875 is equal to 7 times t times the natural log of e, which is just simply 1. I'm sorry, that shouldn't be t, that should be an r. I'm losing my mind. Okay, and then r is going to be equal to the natural log of 2.398875 divided by 7. And then what I will get for r is 12.49999%. And of course, this will round up to 12.500%. And notice how I went it down to the third decimal place. The next couple of problems that we are going to address have to deal with interest rate conversion. Okay, so here we are going to use a given annual interest rate to end the compounding period to find the interest rate per compounding period. Okay, so here we have our interest rate is 365 and we're compounding daily. Now the interest rate per compounding period is going to be equal to I, and I is equal to the interest rate times the number of compounding periods. Well, since we're compounding daily and there's 365 days in a year, we are going to divide R by 365. And that will give us, well, for R, we have 3.65%. Divide that by 365. And we have that the interest rate over the one compounding period is going to be equal to 0.01%. Okay, what about 4% compounding monthly? Well, if that's the case, then M is equal to 12. And R, of course, is equal to 4.8%. Okay, that means that I is going to be equal to our annual rate divided by 12. And that will be 4.8% divided by 12, and that will give us 0.04% per month. Now for this one, we are going to suppose that the interest rate compounding period is 0.02 cents per week, 0.02% per week, and we want to find the annual rate. Now this right here, the rate per compounding period, this is equal to I. Okay, since we're compounding every weekly, M is equal to 52. Now remember, we have that I is equal to R divided by M. However, we are looking for R. We have I, we have M, so basically we want to rearrange this equation so that we can solve for R. And that can be done by multiplying both sides by M, and then we will have that R is equal to I times M. Okay, cool. Well, I is 0.02%. M is equal to 52. And multiplying these two together, we will have 1.04%. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. Stay tuned for our next video, which will go over the average percentage yield and some applications. Until then, this is Bob Boyle, signing off.